In this video, we will talk about race conditions, um, which occur actually when you have two different threads, two or more different threads accessing the same memory address, and where at least one of them is accessing that memory address in write mode. This yields absolutely to unpredictable behavior to an erroneous value being stored in that memory address eventually. Um, an example on this is this piece of code where you have a shared variable total that is defined outside of the pragma OMP parallel for region, and that inside your parallel for, you are having this shared variable to the left of the equal sign. It means you are accessing, the threads will access it in write mode. They will change this variable. Let's see in depth what would happen behind the scenes. So even though this instruction seems to be one single atomic instruction, well, you have to remember that it's not really the case. Either you have already seen this in computer architecture courses, or maybe if this is completely new to you, please bear in mind that this line number 5 would be translated into multiple lines of low-level code. So for the processor to be able to execute this line of code, it would first load the value of total from the memory by accessing the address of total. So using here the @ symbol to denote an access to the RAM or to the memory. So the CPU will load this value first to a certain register inside the CPU, will load the value of I to another register to be able to perform the addition of R1 and R2 finally. Okay, just because the CPU cannot make the add instruction right away inside the RAM. Okay, so it needs to perform this instruction, add on the registers the values that are locally stored within the registers of the CPU. So the add instruction would also take another third parameter, which is the destination of the final value. Suppose it's called R3, and then a store instruction that saves back the value, the final value to a certain address in the memory. It happens that we want to store it inside total. So maybe these lines of code, even if they are new to you, they will show you how actually this line of code is interpreted at the low level, and how really the total value for this occurrence of the total variable name at the left-hand side of the equal sign denotes a value that is different than the value of denoted by the variable name when it's used to the right-hand side of the equal sign. So as if this is total at total prime after the execution of the instruction, and this is the original value of total, or let's say it's total t plus 1, and this is total at the time t before executing this instruction. Okay, so you got used to it, but maybe you have never thought about the internals. And now the question is, what would happen if two different threads, thread 1 and the thread 2, um, happen to execute the same instruction number 5 at the same time? And what if one of them is paused or interrupted amidst the execution of one of those lines? So suppose that thread number 1 has only executed line 5.1, okay, by just loading the value of total from the memory into the register R1. So suppose that total is still equal to 0, and that thread number 1 is taking care of the iteration number 0. Okay, so at that moment, the value that is loaded for total is equal to 0. Okay, so inside the register R1, we will have 0. And this register belongs to the context of execution of the thread number 1. Okay, so it's even if it's the same piece of code, but you already know that those local variables that belong to, or registers, sorry, that belong to each thread, they would be different copies. So what about thread number two? So if thread number two comes into play and start executing its piece of code here, total equal to total plus one, suppose it does the calculation all at once, well, it would load the same initial value of total, which is zero, and then increase it by one to have one finally in total. Don't forget that when thread number one resumes the execution, starting from L5.2 up to the end, it would have already worked with the copy that it has already loaded in R1, which is zero, and then finally it would store the same value one into total. And then it would have missed one of the uh, iterations, effects, or one of the ones that we should have added to the final total, and we will end up absolutely having a total that's strictly less than n. It's not equal to n, okay? Because what's expected here is clearly to have, we're executing this piece of code from 0 to n minus 1, so we're expecting to have 1 times n at the end inside total, so which is equal to n. Here we will have something that is eventually less than n. If this misfortunate occasion does not happen, so maybe if you run your code multiple times, you will always have n, but you have to keep on running it again and again, and eventually you will have this problem. If you don't have it easily, so you can accentuate this problem by cutting it into separate equivalent lines, something like put in temp the value of total, put in temp actually the value of temp plus one, and then store back the value of the new value of temp into one. Okay, so this is 100% equivalent to this line of code, but just to accentuate the effect and the possibility that any of those threads would be interrupted at this phase, especially that certain programming languages would handle such instructions, addition instructions, as atomic instructions by default. Okay, so to avoid or to accentuate this error, just put these three lines, and furthermore, you can also add certain instructions to make certain time pauses. So sleep for a certain number of milliseconds, even a few milliseconds, this or just called yield or something like that, and then you will see that if the thread takes systematically pauses between these two different instructions, then maybe it'll end up having a very damaged value in total. Okay, and it would become almost systematic. Okay, so now the question is how to solve this issue. Well, you have to define a mutual exclusion, critical section piece of code. So this mutual exclusion condition should protect your data from braces by serializing the code and by asking the threads to get one after the other into a certain section of the code. So here we have to define this section of code as a critical section to make it a race-free block. It will become a serial block that is only executed by one thread after the other. Okay, so there is a guarantee that even if a thread finishes here at this moment, well, it has to wait and does nothing until this first thread finishes executing this piece of code for it to resume its execution. So this would define multiple lines with multiple variables declared as a critical section. So this can be done using the critical keyword and the braces to delimit that zone, because it's not recommended to make a very large zone of your code as a critical, because otherwise this large block of code would run finally sequentially and you will lose the importance of your parallelization. So what would be the effect? Well, actually, the effect is that even if at a certain moment thread one would only have the time to initialize this variable with zero, and it had a certain scheduling interruption to give the execution to thread number two, Well, because the section has been declared as critical, you will see that the thread number one has already locked this line of code or this block of code, would have already logged the line number five. So even if the execution is transferred to thread number two, so thread number two can progress on this for loop check, on the incrementation, anything else it wants. But once it reaches this block of code, well, it has to wait on the line number five. It cannot enter line number five, even if it remains multiple iterations or multiple cycles of time waiting and wasting its time. But for the sake of having a good result at the end, a logically accurate result, that thread should wait its turn. So in this case, the execution would be handed to thread number one, which will actually finishes its work correctly, free the lock of the line number five, and only then the thread number two would be able to get back to the its runtime and allocated time, and then lock the line number five once again before any other thread gets in, and then start applying its line of code. Okay, so well, this lock here would prevent thread one and any other thread from taking the lock on it. Okay, just one single information. Suppose you had thread three that comes meanwhile, it will also be blocked. And when you unlock that lock, okay, so when this critical section finishes, we don't know which one of thread two or thread three would resume the execution. So even if thread two was the first one, in so many cases and in almost all parallel programming languages, there won't be a guarantee over the order, or so often you will see that it's a first come first serve order, while thread two will be delivered first. Okay, so you have to read more about your parallel programming language to see what is the effect of the wait and the free for each thread. So another way to handle mutexes is to actually um, declare just one specific scalar instruction as atomic. So in this case, it's it's a way to optimize the lock and the waiting time of all the threads. So instead of declaring a whole block, just focus on the instruction that you have in hand. Okay, so this is equivalent to the code that we had earlier. Okay, so a critical section with only one line of code, okay, is equivalent to this atomic part. Okay, but the extra feature, let's say, of the critical section is that you can define for multiple lines of code, not only for one single line of code. Okay, so the atomic has the same effect as the critical, except that it only applies to one line. So the critical is more generic. So let's see how we can handle or implement mutexes using a thread private variable where to avoid actually the need for synchronization, and then a mutex access to a mutually exclusive access to a shared variable with a critical. So in this example, we are making a sum of the elements inside an array. So we're defining a parallel section from here to there. We are defining two shared variables, which are the array and the final sum itself. But we're defining cleverly a private local variable, okay? That's called local. We are initializing this local variable that is private to each thread to 0, and then we are executing the for loop. Inside the for loop, we are making the partial summations of the AIs that correspond to the iterations number I that were allocated to each thread into a local variable. So each thread would have a different local partial sum, okay? But then before leaving the parallel section, we would make a critical section inside which we are accumulating the partial local sums into the global shared sum variable. Okay, so this is really useful actually, because you're giving the threads the total freedom to make their to execute their iterations and calculate their partial sum really in whatever order they want. And then you are just synchronizing with only one instruction really at the end. Okay, so if you check the results, you will find that without the critical directive, the value would be sometimes correct, sometimes erroneous, but with the critical directive and the synchronization that is done, the value would be systematically correct. Another example in which we are using a thread private variable and a shared synchronized variable with atomic um, is the following. It's an example in which we are summing up the value of I, the value of the iteration number, um, with a certain total. Okay, so we're defining two different totals: a global total, a global shared total. Okay, in which we will have the final total of all the summations, and a private partial total that we are calling a thread total or total per thread. So defining it inside this pragma OMP parallel zone, we're using a for loop to accumulate the values of i's, the summation of the values of i's inside the local private total per thread. And then finally, using this atomic directive or clause, we're making sure that those partial sums are summed up back inside the global shared total in a synchronized way. Okay, so you can see that no matter what n is, even if it's equal to 1000, suppose you have let's say, static scheduling. So if you have 4 threads or 5 threads like here, and each 200 values are summed up with a different thread, well, all these summations can be done in parallel. Okay, the threads can make a, um, good progress really in parallel to compute those partial sums. And the variables, the x variables here, x0, x1, 2, 3, 4, these are actually the thread private partial sum, which is total total threads. Okay, so we can talk about total thread number 0, total thread number 1, total thread number 2, 3, and 4. Okay, so I have 5 different copies of this local private variable that accumulates the partial sums. And then finally, when we reach this atomic instruction, you see that we have a guarantee that the instruction is not executed in parallel, no matter how many cores do we have. So all the threads would be synchronized at this moment, and they will execute this instruction one after the other to guarantee that we finally have the right answer in the total variable. And the answer here is actually it's equal to the summation of all the values of I starting from 0 up to um, uh, um, n minus 1, which is 1000 minus 1, which is 999. Okay, so it's the summation of the first 1000 integers starting from 0. Um, so do we need to use either atomic or critical? Well, actually, there is another solution when it comes to such typical pieces of code. So if what you are writing is in fact a certain reduction using typical operators such as the plus operator, the minus operator, the multiply operator, the min function, the max function, okay? Then this would be considered as a reduction, okay? So again, what's the idea behind this? So suppose that you have to do the sum of all the values inside a certain array, or you want to subtract all these values. So well, actually, it's just the dual. You can rewrite it as an addition and then subtract at the end. Suppose you want to multiply all these values by a certain specific value, or just multiply all of them together. You want to find the minimum or the maximum of all these values. Well, in this case, um, each thread can find the minimum locally, okay, and then communicate that minimum to kind of each other or to the main thread, and then make sure that that communication is done synchronously. So they communicate the minimum one after the other, and then you check that if the, let's say the minimum here was a 3, the minimum that was found here is 1, and the minimum of those values was 4, then clearly the final minimum would be equal to 1. Okay, the same applies in case you have additions or multiplications or maximum, etc. Okay, so in all these cases, when you have a shared variable in which you want to obtain the final result of a certain reducible operation that can be actually cut into partial operations, well, we can use this keyword reduction, and we can specify the operation that you want to perform and on which variable it's done. We can have this for multiple variables. Yani at a certain moment, we can have a for loop within which we are accumulating all the sums of the variables inside a certain array into a variable called total, and we may multiply all of them and store the final result in a certain variable called the product. Okay, so this works exactly. This is a simulation of the code that we saw here. Okay, or the code that we saw there for the shared a thread private variable for the partial sum or the partial multiplication product or the partial minimum, and then a shade with a critical or with atomic for the final reduction for the final global total or global product or the global minimum, and so on and so forth. So let's see a couple of examples. So here is another one where we are working with an array where we have initialized the array with 3.5 times the value of I, and then we have this pragma OMP parallel region with the array being shared, and where we have clearly declared that we want to make a reduction over this shared variable sum using the plus operator. Well, in this case, the code is really much cleaner than using local variables for the partial sums, and then making sure that we have a critical or an atomic section for the final sum calculation. So you can compare it to this one, and you would see how much we simplify the code. Of course, if your operation or the calculation that you want to make is not cannot be defined as a reduction on one single variable, well, then it's up to you to think about the details and to use the best way to synchronize your code using the critical section or maybe a few atomic clauses. Another example in which we are doing dot product of two different arrays. So here we are summing up all the AI times BI for two different arrays. So this code is sequential. And if you want to make it parallel, right, then you have to add this line. But look at the beauty, we can add just one single line. So we want to create a parallel zone for a for loop with a reduction over the sum variable, shared variable, using the plus operator. So just one line of code and it tells a very long story. Okay, so to this, the behind the scenes, the summation would be made partially using local private variables over each value for each iteration within each thread, and then correctly the final sum would be uh, 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 gathered in this variable conveniently in a synchronized way without even needing to write all those details. So this is the sugar added syntax of OMP when it comes to reductions. As I told you, you can define arithmetic operations that can be reduced, and from partial to global sums or minimum or maximum. You can also define this for logical operators. So suppose you want to make the end of multiple booleans, okay? So you can, or the or. You can also do bitwise operations such as and, or, and XOR using these operators here, okay? Well, this concludes the discussion for the reductions. One word that we have about barriers. So do you still remember that when we have braces, this is an implicit barrier. Okay, so all the threads should wait until this closed braces is reached, and then afterwards the main will be able to execute this line of code. So if you have a printf done here, okay, so we will have it really at the end because all the threads would have finished their execution before the main thread would be able to execute this line. But what if we want to create temporary barrier inside the parallel regions? So we can use the OMP barrier close, okay? So at any moment, if we have multiple threads and each one of them is displaying this line and then displaying that line, well, you will see that all the A lines, okay, will be neatly displayed before the the B lines. Okay, so all the A lines would be displayed before the B lines, even though certain if certain shade variables such as x, which is clearly shade, is changed inside the loop. So outside of the loop, it's equal to 2, and inside sorry, outside of the parallel region is equal to 2, and inside of the parallel region is equal to 5. Well, you would see that sometimes the thread number 0 would be able to execute this line, okay, and would be able to change the value of x to 5, so that all the other threads would see it from that moment as being equal to 5, even if the threads didn't reach this section here, okay? So the synchronization is done okay, but if you have shade variables, then you do not guarantee at which moment those variables would be changed, and at which moment they would be actually would take effect actually and would be seen by the other threads. Okay, so as you notice here, only thread number 0 is displaying x equal to 5, so the others are displaying this sentence A. So the thread number 0 is not displaying this sentence A, okay? And afterwards, 0 is displaying with all the others the new value of x with this letter B. So neatly, all the B's are being displayed after the A's, as we said, because we have here an explicit barrier. But because the thread ID 0 may change this X to 5 at any moment, so maybe some of the threads would see this value to be equal to 5, even though they are still executing this instruction, this A instruction. Okay, so just um, um, another information that I want you to know about the behavior of barriers. Well, you have some extra clauses, directives, and ideas that you can read from the online documentation of OpenMP, such as how to declare parallel sections with multiple sections inside it, as the name says it. We already discussed the single clause to make sure that within a certain parallel zone, we have one single thread executing a certain section of code. You can also define parallel zones using the task routine. So check how this can be useful sometimes. We talked about the no wait that fights actually the implicit barriers. So instead of waiting on the closing braces of certain for loops before jumping to the next for loops, if you add no wait before the braces, then you make sure that the threads won't wait for the others until they finish the first for loop. They can directly attack other iterations from the next for loop. You can check task wait, flush, and order on your own by reading their documentations. And you can also check other data scope um, um, uh, attribute clauses or directives such as default to declare all the variables to be shared by default, or to make a copy of the um, uh, first uh, initialization value of a certain variable before making copies of it as private variable into the various threads, or to make sure that a certain private thread um, um, is copied back to the larger context after the end of a certain loop, and to make sure that really the last value that was calculated at the last iteration by the last thread is actually the one that is copied outside of the scope. You can also use copy in and copy private for other purposes. So to summarize this chapter, we have talked about shared memory and multi-threading, the multi-threading model. We talked about the fork join concurrency model and how it is implemented using OpenMP. And we showed how private and shared variables are handled by OpenMP. And then we showed the specificity of OpenMP and its simplicity in handling loops while allowing us to create mutexes using critical and atomic. And then how this can be made even easier, further easier with reduction operators, and how we control barriers, explicit barriers to synchronize the threads in case they are finishing their work and at deferred time. For more info, you can consult these links that redirect you towards the OpenMP reference documentation from the LLNL. And I hope this concludes our discussion about OpenMP and gets us ready for the next parts of the course. Thank you.